just so just a bit about exoplanets. Trying to get rid of my thing here. Currently, there are, this is data as of yesterday, so just over 4,000 exoplanets. So these are planets around other stars that we know of. About 1,400 are Neptune-like, meaning size and density. About 1,300 are gas giants like our Saturn and Jupiter. About 1,300 are super Earths, so similar to Earth, but larger. And about 160 are what's called terrestrial, so those are hard rocky planets. And in this data log, there's about 8 that they, or 6 that they just haven't completely categorized yet. So exoplanets are detected by these 5 major ways. The most prolific one is the transit method, which is shown by, so we have years across the bottom and numbers on the y-axis. So over the years, the transit method we can see has been most prolific in finding exoplanets. Next is the radial velocity, these red ones. I'm going to go through each one to tell you how they actually work. Microlensing are these few here at the bottom. Direct imaging are even fewer, and you can't even see the purple for the timing ones because I believe it's only 2 so far that have been found by timing. So a transit method, if a planet crosses in front of the star, the brightness of the star dips by just a small amount. And this depends on the relative sizes of the star and the planet. So we can determine a planet's radius by this transit method. The most prolific one was in 2009. The Kepler mission went out it was a telescope, we see on the bottom here. It looked at about 150,000 stars in this area of the Milky Way. So here we have the Milky Way that we see in the summertime. Right here is the center of the Milky Way. And this was the area that Kepler was viewing. So it looked at 150,000 stars in this area every 30 minutes and logged the luminosity or the brightness. And if we look from, so here's a bit of a tilted look at our Milky Way with our sun being here, and Kepler was looking out towards this way. And the Kepler mission over 3 years discovered most of the exoplanets we know of. Here's just a look at the systems discovered by Kepler, comparing it to our solar system. So there we have our solar system. This is Uranus and Neptune's orbits. And then we see some are different, very large planets close in, things like that. So Kepler is really good at looking for very large planets going across very small stars, because that ratio really lets the brightness drop. So, and here's just another Kepler orrery looking at some of the systems that Kepler has found.
Colleen, are we just, why are we looking for them? We just point the telescope at a random star and hope we see an exoplanet, or is there an order to it?
Well, in this case, this was the first very systematic one, the Kepler mission. So it looked at this area for over 3 years, looking at 150,000 stars every 30 minutes. So it's found about 4,000 of the known exoplanets. That's just in a very small area of the sky. Again, and I like this one, just looking at all, you can see some orbit very slowly. Some of these planets, some orbit extremely quickly. There's lots of systems that have more than one planet, up to 8 we've now found. So the second way of finding planets is looking at the radial velocity. So a star with a planet, the star will actually move in its small orbit in response to the planet's gravity. And this leads to variations in the speed of the star towards and away from Earth. So here we have Earth, we're looking at this star. We can see that it actually goes away from us and comes towards us. And this is just a graph of that velocity changing over time as it goes away and then comes towards us. And this gives us the radial velocity with respect to Earth. So it's line of sight velocity. It is dependent on the planet's mass compared to the star's mass. For example, our sun moves about 13 meters per second because of Jupiter. So the mass of Jupiter is tugging on our sun. So about 13 meters per second for Jupiter, but only about 9 centimeters per second due to Earth. So much smaller mass, much less variation. This is, again, best for finding very high mass planets orbiting very closely to low mass stars. So that effect will be at its maximum. About
Are you having a break?
I'm just doing a class call.
Oh, you are.
About 500 exoplanets have been found this way by radial velocity.
That's fine, don't worry about it.
The most massive planet found this way weighs 13 times the mass of Jupiter. The least massive found this way is about 2.5 times the mass of the Earth. The longest period, or the longest orbit that has been so far found, is 38 years. And the shortest period is 31 hours. And you can imagine that planets or stars with multiple planets would have very, very complicated patterns. And in fact, this is, so here we have our sun. This is the pattern of the sun over the last 50 years or so. So I'm just going to, so at the center of the sun, we're at these, I'm going to show you the center of the sun from the year 2000. And as all the planets are tugging on the sun, this is where the center has been, the motion that it's done. So 2000, 2008, 2010, going up to 2020. So that's the orbital, or the orbital motion of our sun in respect to all the planets that are tugging on it. So if we see other exosuns moving in really kind of wobbly positions, we have to kind of tease out how what kind of planets it would have to produce those results. This method only gives a planet's minimal mass, but if we can combine this with the transit method, which determine the planet's size, we can then determine a planet's density and some maybe of its physical structure. Another way of finding planets is by microlensing. Excuse me.
Colleen, back to the one. You mentioned that they could determine kind of what it might be made out of.
Yes.
Now if it was heavier, it might not be affected as much by the gravitational pull. Would that be?
Well, the heavier a planet is, the more the sun would be affected.
Yeah, the more it would be. Okay, yeah, right.
Yeah. So by transit, we can discover its size, and by this radial velocity, we can discover its mass. So then we get the density, and then we can start making suppositions of what the planet is like. So gravitational microlensing, this occurs when the gravitational field of a star acts like a lens and magnifies light of a distant background star. So here we are on our Earth. We have a star here with a planet, and we have another star in direct line behind this star, So this foreground star will act as a lens for the light coming off of this background star, and it will bend the light a bit. And if that star has a planet, there'll also be a very small micro lensing event as this far star light passes by that planet. This requires highly improbable alignment. So to find any of these, you need to look at a large number of distant stars and monitor them continually. And it's most fruitful for finding planets between the Earth and the center of our galaxy, because there's lots and lots of background stars there. And so we can use this, there'll be a lot more chance alignments like this. The notable disadvantage of this method, which really makes it pushing the edges of science, is that it cannot be repeated. Because of course, we're moving, this star and planet are moving, and this source star are all moving. So it's not a repeatable observation, which is unfortunate. One of the most exciting ways of finding planets is direct imaging. Now, planets are extremely faint light sources compared to the stars they orbit. And what little light that does come tends to be lost in the parent star's glare. So in general, it is very difficult to detect and resolve them directly from their host star. Planets orbiting far enough from the stars to be resolved, so we're getting away from the glare of the star, unfortunately, they will be reflecting little light, so then they are, increasingly hard to find also. However, if planets are still forming, they'll be radiating mostly in infrared light or heat, and they'll be brighter than the star in that infrared light. So that's planets far away from stars. If they're emitting in infrared, that's a good thing. What is needed are called coronagraphs. So this would be this structure here. This is actually in the telescope, so it blocks the parent star's light so that we can only look at the planets. So these are actual images of planets. We have a little star here. The system has 3 planets that we can see easily. Another system done by a different telescope, but using the same sort of thing, shows a nice planet here. Here's a very large coronagraph, so we're blocking the light from this star, but it's a special type that actually the starlight is interfered with itself, so it kind of cancels that out, and so the starlight is canceled out, but we can see there's a planet right there.
Colleen, well, the new telescopes that are going up, will some of these images become clearer? Like the one of the exoplanets back there, like with the James Webb telescope, will it be picking up like how much different will it look, or how much clearer will we be able to see things?
It will be amazingly better. Yes.
Oh, really? Yeah.
Much larger telescope, so it can collect more light. It's also views mostly in the infrared. So again, these warm planets, it'll really be able to pick out much easier.
Mm.
Yeah. And here's a direct image. So this is a very, very bright star, but we can actually see a little tiny planet beside it. Timing is used with pulsars. So a pulsar is a neutron star. It is small and ultra dense remnant of a star that it has exploded as a supernova. They emit radio waves extremely regularly as they rotate. Pulsars can rotate at up to 800 times a second, down to the Crab pulsar is 33 times a second. And these are extreme, so it's just, these stars are just spinning, and they're extremely accurate in their timing. So if you do notice a bit of timing difference, and this is to the thousandths to millionths of a second, if there is a difference, it could be because of planet. Planets were not, the very first planets were found around a pulsar, but the gentleman who found them did not publish because at that time it was thought there's no way a planet can exist around a star that blew itself in a supernova. So these planets might actually be formed from the supernova debris and not, they weren't planets that existed around the large star and still exist once the star went supernova. So just like we saw in the timing, the pulsars will move a bit in response to the planet's gravity, which changes the timing a little bit, and therefore we can deduce that there is a planet around it. It is very, very sensitive because of the extreme regularity of the pulsars, and it can actually detect planets down to 1/10 of the mass of the Earth, which no other method can at the moment. And it's very good for detecting multiple planet systems. There are two big drawbacks. One is that pulsars are relatively rare. And again, there seems to be some sort of special circumstances for these planets to form around a pulsar. Therefore, it's extremely unlikely that a large number of planets will be found this way. And certainly they will not be conducive to life. Pulsars emit high intensity radiation that would just wipe out any life found on Earth that tried to exist on one of these planets. Those are the ways that the main ways we find planets. Here's just a couple planets that we can look at. So this is the star nearest to us, Proxima Centauri. It's about 4 light years away. It was originally, the planet orbiting it was originally found in 2016 and has been confirmed this year. So here we see the star, and just compare that star to our sun. So it's a much smaller star and a much cooler star. This is a hypothetical visualization of the planet. From what we know from its size and density, we suspect it's a rocky planet. Comparing this planet to Earth, it's just a little bit larger. It's a super Earth, just over 1.27 masses of the Earth, and it just a little over 1 radius of the Earth, so just a tiny bit larger. Its orbit around Proxima Centauri, so here we have that little red dwarf star here. This planet is in that habitable zone. So this is the region of this star, from this star, that liquid water can exist. So this planet is in that region. Comparing it to our solar system, the star and this planet are well within the planet orbit of Mercury. And this planet orbits Proxima Centauri in 11 days. So very close to the planet, but in that habitable zone. But meaning so close that it will be tidally locked. So you'll have one side hot and the darker side much cooler. Here's one of the newest exoplanets found in a star. This was found in the Kepler data. So here is our sun.
This was
graph
just found, wasn't it, Colleen?
Pardon me?
This one here, I was reading about this the other day, I think. Like this is brand new, this one.
This is brand new, yes, yeah.
Cool.
Our sun, our habitable zone where we find our Earth. And we see it's a nice, this represents the temperature, so a nice temperature for liquid water. This star is Kepler 160 is a little bit bigger, a little bit cooler than our sun. And 4 planets have been found. 2 are gas giants. This star is about 3,000 light years away. And this has come out of the data, this KOI planet, that means Kepler Object of Interest. So it hasn't been confirmed as a planet. They're still having to do some more studies of it. It is likely a rocky planet, almost 2 times the radius of Earth. And it has an orbital period, so its year is 378 days. So it's very similar to our Earth in a lot of ways. It still has to be confirmed though. And it was detected by the Kepler mission, so by that transit. Every time this planet went in front of the star's luminosity or brightness just dropped just a little bit. So that's just how exoplanets are found, and a couple of the newest ones. Are there any questions about exoplanets? None?
This current exoplanet, this one? Yeah.
Yep.
How far? I didn't catch how far away this one is.
3,000 light years.
Ah, it's pretty close.
Very close, yes.
As far as light years go, we're doing all right.
Yeah, it's a next door neighbor, more or less. Not quite as close as Proxima Centauri at 4 light years, but certainly certainly very close astronomically speaking. Yeah.
So now that they've made this discovery, I imagine there'd be more people doing observations on this object.
Exactly. Yeah.
What would be some other? Would they just be going out around with some of the other ways that you've already showed us, or is that how they found this by transecting? What other things would they be able to do to analyze it better?
I'm not sure how bright it is, so I'm not sure if they can get a spectra, see if it has an atmosphere. So this was found by the Kepler mission. So any other, lots of other telescopes do transits.
Right.
So it would be confirmed with other telescope observations.
And the spectra would be looking at the different wavelengths that might be in this atmosphere to determine the types of gases that are there?
Exactly, yeah.
Okay, yeah. Cool.
Yeah. It's sort of the closest thing to a sun-like star with an Earth-like planet that has been found. I hope it's an actual planet. I hope it can be confirmed.
Sounds like the next sci-fi movie.
There you go. Your trip to KOI.
KOI.
Any more questions? Okay, I thought we'd look at how we know what we know. And we'll be looking at the Big Bang, spectroscopy, distance ladder, the shape of the Milky Way, and how we weigh things in the universe. So the Big Bang. There are 3 lines of evidence for the Big Bang. We have the expansion of the universe. We know that galaxies are moving away from each other. And the farther they are from each other, the faster they are move away. Now the galaxies themselves are not expanding because of the gravity of the galaxy. They're gravitationally held together. It is the space between the galaxies that is expanding. So if you have an expanding universe, you just run the film backwards and you find that everything was all in the same place at one time. And this expansion of the universe was discovered by Edwin Hubble in 1929. So that's the first line of evidence that our universe started with a Big Bang. The second is the amounts of hydrogen and helium that we see. We know that essentially all the heavy elements greater than helium are created by thermonuclear reactions at the center of stars and in stars that go supernovae. But there is far more helium in the universe than could have been created by hydrogen fusion in stars alone. So if our universe just started out with hydrogen, there's way too much helium that we see now that only the stars could create. So using high energy physics, it was predicted that in the first 1 to 3 minutes after the Big Bang, the primordial elements were formed, 90% hydrogen, 10% helium, this is by number, and all observations of the universe have verified this. And the third line of evidence is the cosmic microwave background radiation. This is direct evidence for the Big Bang. It is the faint afterglow of that primordial fireball that filled all space shortly after the beginning of the universe. And this is what that afterglow looks like. So these are showing warm spots in the yellow and red and cooler spots in the blue. Again, these are kind of relative. The difference between the darkest blue and the brightest red is, I believe, 1/100,000th of a degree. So these are very minor differences in the temperature of the universe. And it is thought that these slightly warmer areas are places where there was a few more molecules, which would seed the universe with the galaxies. So in these areas, that's where we're going to find way more galaxies forming, all these areas. And in these areas, that's where we're going to find much fewer galaxies. So very.
Do you know how we're able to measure so accurately the temperature, like what tools we use?
Yeah, this took several iterations. First, there was a satellite called Kobe that went up, and it just had, very large. So this would all be red, all be warm, and this would all be blue, not with these detail. Then that went to the Wilkinson microwave anisotropy probe, which had better measurements of the universe. And this is the final telescope that went up, the Planck telescope. So these are measuring heat. Now this heat is at 2.7 degrees Kelvin, so almost absolute zero. So these telescopes had to be outside the atmosphere of the Earth, and they had to be cooled down by liquid nitrogen to keep them cool so that they could detect heat. So this is the heat of 2.7 degree universe with teeny tiny variations in that heat. Does that answer the question?
It's another one of those times when it's really tough to wrap your head around. Like, so this is a visual, like a representation of the whole universe,
yeah.
And it's warmth and coolness, right? I don't know, the way I kind of think of it, it'd be like kind of like having a balloon, putting a bunch of confetti in it, blowing the balloon up a little bit, and then kind of you pop it. And you have all kinds of different things just heading out in all kinds of different directions, right?
That's a really good explanation of the Large Hadron Collider, I think. You're gonna have to think about that one. Yeah. So this is what the universe looks like at 2.7 degrees Kelvin with little tiny variations. So this is the afterglow. The Big Bang was this fireball that has been cooling down for almost 14 billion years. And just thinking of the theory, it predicted that there would be this afterglow of about 3 degrees. and the observations actually proved it. Okay, we've talked a little bit about spectroscopy, and I brought that kit. I just want to go over really quickly again, because this is the main way we learn everything about the universe. So we start with the electromagnetic spectrum. It goes from gamma rays to radio waves. So gamma rays are very, very tiny wavelengths, very, very highly energetic waves of light. They are so tiny that they can damage the DNA. We go over to X-rays, which are slightly longer, and we all know people who have had X-rays. So they can also damage things, but not as bad as X-rays. And we can shield places we don't want the X-rays to penetrate. Ultraviolet light is what gives you sunburns. Here we have the visible range, very, very tiny portion of the total electromagnetic radiation spectrum. Infrared is heat, and we have infrared detectors on our skin. We go down to microwaves. We're getting now to extremely long wavelengths and very, very little energy. So we have microwaves, and the least energetic wave is a radio wave. The cell towers and things like that use microwaves, but microwaves and radio waves are not energetic enough to do humans any damage, which is kind of good because we use them a lot. So again, Isaac Newton discovered that light bends when it's passed through a prism, and that the amount of bending depends on the wavelength. So this is what we use to examine light from the universe. And the three basic ways of using this information: if we have a light source, we will get a nice spectrum, that rainbow colored spectrum in the visible light. Now remember, this also goes into the ultraviolet and into the infrared, but we're just going to talk about visible light right now. And we all saw that when we had those glasses on, looking at the overhead light to get that nice spectrum. If there happens to be a gas cloud between the light source and our viewing, we will get an absorption line here. So whatever elements and molecules are in that gas cloud will absorb light at a very specific wavelength. If we have the same kind of gas cloud, go down there, same kind of gas cloud, but no light behind it, it will give off an emission line in exactly the same wavelength as this absorption line. So that's how we know everything. When we look out into the universe, when we use spectroscopy, we can see that every element in the universe has its own barcode. We looked at several of those different gases with those glasses. We could see every element having its own barcode. So we can figure out what elements are out in the gas clouds and in the stars. Here I just have a bunch of different stars. So we've got temperature or wavelength, the spectrum across the bottom here. And these stars go from O stars, which are extremely hot stars, down to M dwarfs, and those like Proxima Centauri, small and cool stars. You can see that all the lines of the elements in each one here. So we can categorize what's from the spectra, we can categorize what kind of stars we are looking at and learn a lot about them. The Doppler effect, we all know that from our sound. As an ambulance goes by, the sound is high pitched, and as it passes, it lowers the pitch. We have the same sort of thing in spectrums. So if we have this spectrum from a star, if the star is going away from us, you can see all these lines are shifted to the red end, just a little bit. If the star is coming towards us, all the lines are shifted to the blue end. So that's red shifting and blue shifting. So we can, if we look out, we can see the rotation of galaxies. So the stars coming towards us will be blue shifted. So we get a peak in the bluer area of the spectrum. And the stars going away from us will be red shifted. So we will see a shift over of those absorption lines to the red end of the spectrum. And of course, right in the middle is where there is no radial, there's no line of sight motion. So that's exactly, we get the spectrum exactly as it would be. And this is a real picture of the Triangulum Galaxy M33. And we can see its rotation. It's rotation towards us, not rotating at all, and then rotation away from us. So we can look at galaxies' motion. We can also use spectroscopy to look at binary stars. Lots of stars, at least 50% of the stars in the sky are in binaries, so there's at least 2 stars orbiting around each other. Some of them orbit so close that we can't separate them optically using visual wavelengths. But if we can look at the spectra of that system, we can see that as this, so this is our observing position. We can see that as the stars go away from us, it's being shifted to the red end, and as it's coming towards us, it's shifted to the blue. So we get this spectrum for both stars, and we can see that they are moving away and towards us. So we can get information on the binary stars. We can determine their speed, their orbital period, and their semi-major axis, which is how relates to how big the stars are. And from that, we can get the total mass of the star. Sorry, was there a question?
Yeah, I was curious about, we look at binary stars. It's super interesting. I remember you mentioning that before, but I didn't realize how often it happens. Now, yeah. I'm wondering, is there some that it's more than 2 stars, or is 2 the magic number? Because if there's more, they end up hitting and combining, or
no.
Why 2? Why is there binary stars? Like I know, like when you look at diatomic atoms, they bond up so they can. Yeah.
So the binary are the 2 stars, but they can go up to 6 stars in a system. The middle star in the handle of the Big Dipper is a 6-star system. It's got 2 stars orbiting each other here, 2 orbiting each other here. Those 2 pairs orbit each other, and then there's a 3rd set of binary stars that orbit the whole thing. So it's a 6-star system. So binary, it's just because all stars are formed in these gas clouds. They're formed very close together, and so it's very easy for stars to hook up and become mutually gravitationally bound. Yeah. But up to 6 stars are quite common. So we've got the binary stars that we can find out. We can also measure the temperature of stars by looking at where the maximum light peak of the spectrum is. So we see red stars. These are cool stars. They're about 3,000 degrees. Yellow stars like our sun are about 6,000 degrees. And then blue stars, oops, I want to move this. Blue stars can be 10,000 up to 50,000 degrees. So the peak wavelength that the star emits color in is directly relates to its temperature. And we can also see magnetic fields of stars. So this is our sun. This is a magnetometer that is detecting the wavelengths of the sun, and it's looking right at this slit. So here we're going to go into a sunspot. So the sun itself has this nice wavelength absorption line. And as the sunspot moved over, you can see the absorption lines kind of bend a bit. That's Zeeman lines, and so from them we can tell the magnetic fields of the sun. We also use spectroscopy to figure out what kind of supernovas happen. Supernovas are large stars generally that blow themselves to smithereens. There is a one type of a superstar called a type 1A. It is very important for the distance ladder that I'll go into also. So we need to, when we see a supernova, we need to figure out what type it is and then use that information appropriately. So like you just remember that to find out the most we can about the universe, we need to gather light from all parts of that electromagnetic spectrum, from X-rays down to radio waves. Here we have optical. So this is how we see our Milky Way galaxy. But we can see, so these are all looking at the same part, but in different wavelengths. And you can see that we get totally different kinds of information from each wavelength. So we can really understand the universe better. And this is our sun's spectrum and the 200,000 absorption lines that we can find in it, remembering that that's how we tell what elements and molecules are in the outer layers of our sun. Any other questions on spectroscopy at the moment? We still have time?
Yeah.
Okay. The next subject is distance ladder. So this is how we determine the distance to objects in the universe. The first step is within our solar system, and we can bounce radar off planets and asteroids and certainly get their distance then. The next step up is the stellar parallax. So that's, you know, holding your finger out from your face and looking at it left eye and right eye, and it looks like it moves against the background. We can do that with our looking at stars. We look at the stars in January and then in July, so 6 months apart, and we can see if that star looks like it's moved against the background, and we can determine exactly how far it is in. It's a direct measurement of the distance. Next, we go out to something called stellar parallax, or spectroscopic parallax, sorry. Again, we use spectroscopy. When we're finding these parallaxes in this level, we're also looking at the spectrum of the stars so we can detail how bright they are and what they're made out of, all that sort of thing. So if we want to look out farther, if we can get a good spectrum of any star out to tens of millions of light years, we can plot it and we can figure out how bright it's supposed to be, and then we can figure out how bright it looks to us, and that will give us the distance. Currently, the Gaia Mission is observing 1 billion stars, and we're looking at their parallax and their spectrum, and we'll be able to get distances to 20 million stars. So again, we're moving out a little bit. So this is something called the HR diagram. And if we look at a whole bunch of stars and look at their temperature or their color against how bright they are, most stars will fall along this sort of sinuous line here called the main sequence. That's where most stars spend most of their life. So if we're looking out and we see a spectrum of a star, we can plot it on this diagram and we can figure out how bright it, again, we can figure out how bright it is compared to how bright we see it as, and go from there for distances. Another type of, another Cepheids. So Cepheids are stars that vary their brightness, and they vary it particularly, how bright they get is determined by how long they're expanding their period, how long they're expanding to great. So we see a little star here, very quick period, it just flashes on and off, doesn't get very bright. A star that gets a little brighter has a longer period, and then some of the longest Cepheids. So these are periods of hours to days to months. these are all, like I said, the period of the blinking is directly related to how bright they are. So if we found Cepheids in other galaxies, all we have to measure is how, what the period is, how often it blinks. And from that, we can determine how bright it should be. Again, looking at how bright we see it, we can then determine how distant it is. And this is 1920. This is what Hubble used to prove that the Andromeda Galaxy was actually its own galaxy, and not just a cloud within our Milky Way galaxy. It was actually extragalactic. I mentioned type 1A supernovas. These are very luminous supernovas that can be seen across the universe. And we know how they form and that they are all exactly the same. So we know how bright these should be. Again, comparing to how bright we see it gives us the distance. These supernovas can outshine all the other stars in the galaxy. So here we have a large galaxy, we see all the dust lanes, we see it as a halo of stars, and we see this one star has gone supernova. And at its brightest, it is actually outshining the millions of stars in the center of the galaxy. So we can do that out to, I think I found 10 billion light years away. The important thing about all these distant ladders is that they overlap. So one is always, you don't just have one way of measuring distance, you have overlapping ways which confirm each distance. And there's about 20 other different ways to find out the different rungs on this distance scale ladder. Some of them get really, really esoteric. You really have to know a lot about evolution of stars and things like that. How do we know what our Milky Way looks like? In the late 1700s, William Herschel made a star count at more than 600 different locations in the sky with his telescope. So he just looked out and counted all the stars he could see in this field of view in his telescope. He assumed that all the stars had the same brightness so that he could estimate the distance to each star from the Earth. Of course, this was done way before any realization that stars vary greatly in their brightness. So using his data, he created this map of the whole sky. He put the Earth here. So he was bringing the Earth back to the center of the universe. One of the interesting things is this lack of stars here, which he really could not explain. And it's just looking towards the center of our galaxy. There's so much dust and gas and there that he there could not see any stars. But he didn't know about dust and gas, so he couldn't reason that out. And then in 1917, Harlow Shapley used globular clusters. So globular clusters are these spheroidal concentrations of stars that are all gravitationally bound. They can be hundreds to millions of stars in one glob. He looked at them and measured their positions and distances and plotted against the Milky Way. And he found that they all orbited a common center of gravity. This pushed the sun and the Earth away from the center. If all those things were orbiting something, that must be the center of our galaxy. In our latest map of the Milky Way, astronomers have looked at the distance and velocity of stars and nebula and have come up with this view. So here's just a few of their measuring what they look like: nebulous stars, open clusters, anything that they might see, getting spectra, getting distances, and getting velocities. And when you put all that information together, this is what you get. We are in a spiral galaxy with a long bar at the center. It's yellowish because those are older stars. From each end of the bar, we have a strong spiral arm. And then there are lots of little spiral arms, little chunks, and we are actually in the Orion spur arm, a little chunk of not a full arm, density fluctuation of an arm. So here again, we have that long bar. Here's our sun in the summertime. We are pointed at the nighttime towards the center of our Milky Way. And in the wintertime, we are pointed away from it. So we have many more stars to look at in the summertime than we do in the wintertime. And of course, this is flat, kind of like a Frisbee. So an edge-on view, there's that bulge of those older stars. It's a very thin disk, only about 1,000 light years in depth. The sun is about 28,000 light years from the center. And here again, we see a bunch of globular clusters. So those are orbiting the center. And about 100,000 light years in distance. The newest study has found a warp in our galaxy. So we have an upward warp here and a downward warp on the sun side. And this is probably due to dwarf galaxies orbiting through and crashing into our Milky Way disk. So here we have the path of one of the dwarf galaxies going through. There's probably been about 13 dwarf galaxies that our Milky Way galaxy has kind of absorbed. Every time a dwarf galaxy goes through the disk, the stars are perturbed a lot, and we actually hold on to some of the stars while the rest of them go around. And the last thing is math. Yay! How do we weigh things in the universe? Kepler has 3 laws of gravitational or planetary motion. Okay, the first, or his third law, says the square of the period is proportional to the cube of the semi-major axis of the orbit. What does that mean? It means the period is the time it takes an object to orbit around another object. The semi-major axis is 1/2 the distance of the longest diameter. Longest diameter, all orbits are elliptical, so it does have a long diameter and a short diameter. Semi-major is 1/2 the distance there. And Kepler found that if you took the orbital period and squared it, it is equal to this semi-major axis cubed, divided by the total mass of the sun, or the system. So if we rearrange things, the total mass of the system will be the semi-major axis cubed divided by the period squared. Remember, we can find these out from the transit method, the radial velocity method of looking at exoplanets. We can look at these are really easy numbers to get. So we can actually weigh things. It's how we weighed the supermassive black hole at the center of our galaxy. If you remember, that one star was orbiting it, and looking at its orbit, how fast it went around and how far it was away, told us that what is there is 4 million solar masses. And this can be done for any planet in the solar system. If we look at Jupiter just really quickly, Jupiter is about 5 astronomical units from the sun. An astronomical unit is the distance between the Earth and the sun. So Jupiter is 5 times farther out from the sun than the Earth. So if we cube that, we get about 125. The takes Jupiter 11 years to go around the sun. If we square that, we get about 125. And if we look at all the planets in our solar system, they fall along this beautiful straight line graph. So we know anything that is orbiting the sun, we can predict the time it takes. If we know one, then we know the other. If we know the time it takes to go around the sun, we can figure out what its orbit shape is, and vice versa. And that is all I have.
Wow, that's great, Colleen. Thank you a ton. We'll just go around, guys, and we'll just do a bit of a, okay, what did you think? What blew your mind? And then we'll be out of here. I got to get out of the school in the next 15 minutes.
Sorry I took so long.
Oh, no worries. I had my big numbers thing at the beginning there that went on longer than I was anticipating as well. What'd you think, dude?
I think what was the craziest is how big some of those numbers were. It's kind of crazy to think about how big they actually are. Yeah, I had no idea. I don't know. I think that's the craziest thing, in my opinion.
How about you, Will?
My brain hurts.
Good.
Yeah, I was listening to all of that. I'm just halfway through, I'm like, and I've lost all of it. Because there was just so much. I'm just like, holy man, this is crazy.
And I just touched on the little tiny bit of each of those topics.
I definitely know I can't do that for a job, because I would be screwing up on things, because my brain would just get overloaded, and I'd go, and I need a break for half an hour.
Well, a lot of the people become experts on kind of one thing, Will, and that be like you focusing on just cars, right? They'd be focusing on just a particular aspect of it, and then pick up about the other stuff along the way. Hamilton, you're upside down. What'd you think, man? You're on the roof now.
Just how smart some people are to be able to come up with Skews number, or to think to try to research temperatures that are 0.2 something of a Kelvin to look for evidence of the Big Bang. It's just crazy what people come up with.
And and some of the different ways we have for checking the data, like the different ways we have of making the observations and fact checking, basically triangulating, right? And being oh, hey, we were right. Science
is all about reproducibility.
Which was interesting when you were talking about the stars that act like a lens, right?
Yes.
They can't be reproduced, but it's a phenomenon that happens. So that doesn't disprove science. That just means that it's not reproducible.
That one is not reproducible.
Yeah, that particular one, yeah.
Yeah.
Wyatt, how about you? What do you think, man? Wyatt Clapton.
I think it was extremely good, but my brain also hurts.
Yeah.
Yes.
Jace, what did you find particularly interesting?
That was a lot.
And? I think his brain is frozen. Her brain is frozen. Jared, what do you think?
I think I don't understand anything anymore. I'm really confused by that. There's a lot of stuff just in there. You said you only touched on lightly, right?
Very lightly. Each topic could be a 3-month seminar.
Yeah, I think you are a good example of the more that you know, the more you know we know nothing.
Exactly.
Right.
Yes.
I mean, you start looking at all these ways that people have figured out and all these different things that they've got about the galaxy. And we know a lot, but each individual, we're kind of built on the collection of knowledge of our species over time. Right. And each individual, we really rely on the intelligence of others. So.
And it seems that each question we answer, we only make, 50 more questions.
Now, I kind of think when we look at like the exoplanets and they're going across the sun and they're kind of dancing along, you know, I kind of wonder what type of music might those planets be listening to. And the only thing I can come up to